All right, what up, dudes? Let's do some chemistry tutoring. Here's my basic idea. What I'm going to do is I'm going to do gas law tutoring first, and I'm going to give you guys the basic overview of what's going down, and then I'm going to take field questions, and we'll kind of go over them individually. And then what we'll do is I'll do a little bit of precipitation because it seems like those two ones really suck for you guys. Got it? Now, gas laws is way easier than precipitation. Chapter 5 is easier than Chapter 4. And I think that the problem that you guys are having with Chapter 5 is you guys are way overcomplicating it. At least when I sit down with Andre, it's like, he's like, I don't know how to do this. And he does all of these crazy things. And then I'm like, dude, you did like the super complicated route to something that is super easy. All right. So in class, I developed for you this equation, PV equals nRT. Oh, wait, you can't see that. PV equals nert. Perv nert, right? All right, so this is about the highest you can see. All right, you guys got that? Now, P stands for what?
Pressure.
Pressure, say it loud.
Pressure.
Pressure.
Volume.
Volume.
Mole.
Number of moles, it's like the number of stuff you have in there.
Okay.
What is R?
Universal constant.
The universal gas constant and
Temperature.
temperature. Temperature is measured in this equation in what?
Kelvins.
Kelvins. If I give it to you in Celsius, what are you going to have to do?
Add 273.
You're going to have to convert it to Kelvins. That's pretty easy to do. Just add 273 to it. Technically, it's 273.15, but, you know. This right here, R, is actually, you can look it up, but I'll give it to you now, 0.08206 atmospheres, ATM, liters per Kelvin mole. Got it? So, pressure, if I'm using this R, then pressure has to be measured in what? Atmospheres, because the units of R has atmospheres in it, right? I can't have units of mmHg over here if I'm using this R. So if I gave you mmHg or torr or pascals, what would you have to do? Convert it to atmospheres. Got it? What about volume? What is volume apparently measured in?
Liters.
In liters. So if I gave it to you in milliliters or cubic yards or I don't know, something stupid like was it cups or quarts or gallons or whatever, what would you have to do?
Convert it to.
You have to convert it to liters somehow. All right. So this R kind of forces us to use specific units on the P, V, and T. No one really messes with your N. Actually, there are very many ways to mess with it, and I take that back. This is the number of moles. If I gave it to you in grams, you would have to use the molar mass to convert that from grams to moles. If I gave it to you as a volume, and I told you the molarity of something, you would have to use the molarity to convert it from liters to moles or something like that. But then again, we're dealing with gas, so I'll never give you a molarity because molarity has to do with solutions. Like liquid solutions as opposed to gases. But I could theoretically give it to you as grams. Does that make sense? And then you have to convert it. So, is this hard? Perv nert. I don't know why that helps me memorize. It's not even a word, but yeah. It always makes my students giggle, and that always makes them memorize things.
It's close to a word, that's why.
All right, perv nert is your gas law thing. And so here's the idea that we kind of came up with. We said, all right, well, if PV equals nRT, then can I write this? PV over NT is equal to R. You guys are going to have to get very good at throwing N's and T's in the denominator and all of that kind of stuff. Am I confusing anybody with this? Emily, what did I do here?
You just put the symbols on the other side, but it's like the same equation.
Right. How did I do that? Like, why am I allowed to do this? I'm trying to get R by itself. I just divide by N and divide by T. That's why it's in the denominator over here. Is everyone cool with this? Cool? All right, so the concept is, if I have this equation here, and if I have some gas over here, and I have the same gas, but I have it in a different bottle, got it? Then the pressure might change, the volume might change, the number of moles might change, the temperature might change, but I'll tell you one thing that hasn't changed. The R. Why? Because it's the universal gas constant. It's universal. It works for this one, and the same R works for this one. Does that make sense to you? So, in this situation, I could have pressure 1, volume 1, number of moles 1, and temperature 1. And in this situation, I could have pressure 2, volume 2, number of moles 2, and temperature 2, but it's going to be equal to the same R. I'll tell you what that R is. It's 0.08206 atmosphere liter per Kelvin mole. We cool with that? All right, now here's the big concept behind this thing. Since this is equal to 0.08206 atmosphere liter per Kelvin mole, and this is equal to 0.08206 atmosphere liter per Kelvin mole, can I just say, well, then this is true? If this is equal to R and this is equal to R, then they're equal to each other, right? I can't see the question to this. Why
do some people say R equals 8.13?
Oh, okay. Cameron, you looked it up on the internet and you said that, oh, hey, R is 0.813 or something like that? I can't see that. 81345?
Yeah.
All right. The reason being is because they probably, I'm telling you that R is measured in 0.08206 atmosphere liters per Kelvin mole, but when you look it up on the internet, you might find a different number, like 8.3145. And the reason being is because look at the units of the thing that they told you R was. They probably said, oh, that's 8.1345 torr liters per Kelvin mole or something like that. They probably gave it to you as a different units. And usually the unit they would change is this one. So for our class, we're memorizing this number. Actually, I don't even care if you memorize it. I just want you to be able to look it up. And then we're converting everything over to atmospheres. You could decide to only deal in mmHg. And in that case, you would, change this number by converting atmospheres to torr or mmHg, and you would get a different number. Does that make sense? Okay. All right. So this right here is kind of like these two equations are your big equations. This is number 1, number 2. Write them down. But really, number 2 isn't really that different from number 1. Actually, number 2 is exactly number 1, just written a little bit differently. Does that make sense to you? I got number 2 from number 1, so it's really just me rearranging number 1, and I get this magical new equation, but it's not really new. All right, now the thing that you're going to do in your homework is this. You're going to say, they're going to give you one scenario, and they're going to give you another scenario, okay? And they're going to say, well, I kept the number of moles the same, and I kept the temperature the same in the process. But I changed the pressure and the volume throughout the problem, okay? So it's kind of like this. If I have P1, V1 over, I don't know, let's say the number of moles is 2, and the temperature is 3 Kelvin or something like that, okay? I'm just making up numbers. And I say over here, I have a different pressure and a different volume, but I have the same number of moles in there. I didn't add any gas to this system. That would be changing your moles, right? You would pump in some gas or pump in some air to the balloon or something like that. So I didn't do that. I just, moved the balloon from one space to another. I didn't change the amount of gas I put inside there. And then you kept the temperature the same, In this scenario, if this number and this number, how do I get rid of this fraction? Well, it's being divided now. I can't divide it. I cancel it by
Timesing.
multiplication. There we go. Yeah. So I multiply that by 2, and I should multiply that by 2 just to play fair. And look, those 2 cancels out. There was no point in having those 2's in the first place, because there was a divide 2 over here and a divide 2 over here. Does that make sense? And also the same goes for the temperature. If the temperature over here is 3 and the temperature here is over 3, can I just cancel this out? Since there's both divide 3's on both sides of this equation. Are we cool with this idea? So look. Is it right if I just wrote that down? This is assuming that n and t are the same in both scenarios.
Yeah.
Cool? This I introduced to you as Charles' law. No, this was Boyle's law. I think this was Boyle's law. Boyle's law. Got it? Now, I don't want you to memorize Boyle's law. See, I don't even remember if it's Charles' law or Boyle's law. I don't really care. Because really it came from number 2. In the very specific case where n and t are the same. Does that make sense to you? Okay. Let's try this one again, but this time I'm going to keep the pressure the same across the board and the number of moles the same across the board. Okay? So that would mean I would write P1 V1 over N1 T1 equals P2 V2 over N2 T2. But I told you I would keep the pressure the same and the number of moles the same. So I would cancel out those ones. Are we cool with that? So really, there was no point in me writing this right here. Are we cool with that? This I introduced to you as Charles' law. I believe this one's Charles' law. But again, you don't have to memorize this, because if you have number 2, Charles' law basically comes from that comes from number 2 with the very specific conditions that pressure stayed the same and temperatures, or the number of moles stayed the same. Are we cool? And then we'll go back and play this silly game again and say, well, what if the number of moles changed, but I kept the pressure the same and the temperature is the same? Well, how would this change? Okay, well, I've got V1 over T1 equals V2 over T2. We're cool with that? This I gave you, no, oops, I made a mistake. I told you I kept the temperature the same, right? I'm sorry. V1 over N1, V2 over N2. Are we cool with that? This I introduced to you as Avogadro's law, and you guys all freaked out and just be like, another Avogadro thing, my face is going to melt off. And I told you it's not going to be so bad. It really comes from number 2, just in the very specific scenario where P1 and T1 are the same. We're cool? So this is really the only thing you have to memorize. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And really, that just comes from Pervnert. So technically, Pervnert is the only thing you really have to memorize. We're cool with that? Now, how do I solve problems? I'll tell you, it's really easy with this stuff. What I'm going to do is I'm going to give you 2 scenarios, 2 states of the gas. I'll say, here's a balloon, and the balloon has this pressure to begin with, and this volume, and this temperature, or whatever. Okay? And then I let all right, so let's make up a problem. Let's say, here's a balloon, and the balloon has this pressure, P1, and it has this temperature. I filled it up at this volume. See, I filled it up at this volume, V1, a specific volume. And then I let the balloon go up into the atmosphere. And when you go up in an airplane, right, when it goes up into the air, what happens to your ears when you go up in an airplane?
There's less pressure.
There's less pressure, so the pressure changed, didn't it? So it went from P1 to P2. And then I'll ask something like, well, how did the volume change? V2, and I'll just equals what, or something like that. This is my drawing. Are we cool with that? So balloon in scenario 1, balloon in scenario 2, and let's say that I specifically said in the problem that temperature didn't change. Somehow I kept the temperature on this thing the same. Got it? Then, well, and I didn't say anything else. Well, one thing you could assume is that I didn't change the number of moles throughout the thing. Changing the number of moles would mean somehow in letting it go, I let the gas, I put more gas inside of it. That doesn't really make sense in this problem. Does that, you get that? So N1 and N2 are the same. Are we cool?
Yeah. Okay.
It could also mean this scenario that gas leaked out of this thing, which actually could very well be a possibility. But I think that if I didn't tell that to you specifically, then you can assume that I didn't. Cool? So N1 and N2 are the same. Also, I told you T1 and T2 are the same. So from this equation, what would you write down? You would just write down P1 V1 equals P2 V2. Because the N's and T's are the same. They canceled out. We cool with that? Now, what did I ask you to solve for? I have a question mark on the board right next to it. What was I looking for? Come on, people
volume.
online, you guys are not talking.
The volume.
The volume. So I'm looking for this. What's stopping that from being all by itself? I need to solve for it. The P2. And how is it messing with the volume? Is it adding, subtracting, multiplying, dividing? Use your words out loud. It's what?
Dividing.
No.
Subtracting.
No. It's multiplying.
Multiplying.
P2 times V2. That's what I see right there. I don't see a subtraction sign.
Oh.
So how do we fight? No, it's not adding. Ah! You guys are not.
We're gonna go through the whole thing. till we
Half
get
of
it
you
right.
are in my algebra class. Come on. That's algebra 1. You're in my algebra 2 class. Okay, all right, anyway. All right. Yeah, no, it's not dividing. It's multiplying. See, P1 or P2 times V2. Do you see that? Everyone see that?
Yeah.
Okay. How do I fight a times robot? How do I fight the times thing? How do I get rid of the P2? Now, Madison, you can say it. By doing what? Remember, this is simpler than you think.
Show padding.
Ah, you're doing this to me on purpose, aren't you? No, I miss. No, you divide it. If P2 is multiplying V2, then you want to get rid of P2 by dividing it out, right? So divide by P2, divide by P2. And so this cancels that cancels that, and you end up getting V2 is equal to P1 times V2 over P2. And all you do is plug that into your calculator. Keeping in mind, of course, that if I gave it to you in torrs, you might want to convert it to atmospheres. Same goes with P2, and then if I gave you the volume in some kind of funky unit, you'll need to convert that too. Are we cool? Let's do some example problems. And why don't I not do the same example problems that I already gave you guys? Give me a problem. One that you guys are like, I am having so much trouble with this. Why does that work? Why does what work? What are you talking about? Oh, I'm so sorry, I erased it. Here, I'll give you the equations. Ready? Pervner and P1 V1 over N1 T1 equals P2 V2 over N2 T2. This sounds like a really tough equation to memorize, but it's just PV over NT equals itself, and then I just put 1s and 2s on the bottom. Why does what work? It's hard for, well, assuming that the temperature,
And
you have to read it
moles.
to me.
That moles are constant. Is it really true that the volume can change if the pressure changes in real life?
Yes, absolutely.
Oh.
Yeah. The answer to that question is absolutely yes. This thing works. Now, Next week, now notice how this is called the ideal gas law, right? And you just asked me blah 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 real life, right? And so it doesn't sound like this is the real gas law. This sounds like the ideal gas law. And my answer to that is this. You're absolutely right. The real gas law is actually much more complicated, and we'll get into that on Monday, and we'll talk about pieces of that. But for the most part, a lot of gases can be modeled by the ideal gas law. Whereas if you're talking about very specific gases, then small changes need to be made, and we'll on Monday I'll tell you how those approximations work. But for the most part, the scenarios that I'm describing to you, this is how real chemists actually model things. If they want to get a very rough picture, if they need a super duper precise picture, then they use their super advanced chemistry to get better models of the thing. For the most part, PV equals nRT. That's spot on. Is that a good enough answer? So for the problems that I'm describing to you, PV equals nRT works. Now, if we trade out different gases, like I think helium is an ideal gas, but oxygen is not an ideal gas, and there's these small little variations. And if you look at some of the example problems, or if you read your book, they have a whole section on that discussion. But really, this is it. And I think that the reason why I say you guys are way overcomplicating this is because essentially all I'm asking you to do is solve for x. Divide by 4, divide by 4. X equals 5 times 3 over 4. That's the kind of stuff I'm asking you to do. When you really look at it, that's all I'm asking you. Maybe the only other complicated thing I could do is like something like this. 5 over x equals 4 times 3. Or 4 divided by 3. Solve for x. Or how do you do this one? Let's do this one together. You cross multiply, so that would be 5 times 3 equals 4 times x. And why would you cross multiply? Just wondering. Do you know? Why did I go from here to here? Algebra 1, people. Because I don't like fractions. So I got rid of the fractions. I especially don't like fractions when the thing I'm looking for is in the fraction. That's when I really don't like fractions. So I need to get my x up into the numerator because I know how to deal with this. I don't really know how to deal with that. Does that make sense? Yeah. So that's why I moved from here to here. And then this is the same problem. You just divide by 4 and divide by 4 and there you go. You got your answer again. X equals 5, whatever. Got it? You see how this scenario relates directly to this? This would be like if I asked you to, you had P1 over T1 equals P2 over T2, and I asked you to solve for T2. Oh, well, what would you do? Well, the first step you would do is P1 times T2 equals P2 times T1. I just cleared out the fractions, just like what we did before. And then I asked you to solve for T2, right? Is that what I said?
Yes.
So how do I get rid of the P1? Don't say add.
Divide.
I divide. There we go. So then I just divide by P1. There we go. I solve for T2. Done. Good. Madison, I was going to burn you on that. All right. Give me an example problem because I want to move on to the next chapter. I think that for your gas laws homework, that pretty much is like the basic gist of it. And the reason why I'm recovering it is because on Monday, not on Monday, but on last week, Wednesday, I felt like we did a really good job at convincing you that PV equals nRT is a thing using the mosh pit examples, right? And then after that, we, so you finally watched the video? Or you were
No,
there.
I was there.
You were there, right? You weren't there.
Yeah. Maston was there too.
Oh, so it was the three of you.
Yeah.
Yeah. Yeah. So using the I wrote that way too high. Sorry. PV equals nRT. Using the mosh pit videos, or using the mosh pit examples, I proved to you that this was a thing. Actually, I didn't prove anything. It's reasonable. It makes sense in our heads that this is a thing, right? I didn't do any experiments to actually prove to you that this works. But actually, yes, it does work. So you guys were asking, wait, so that mosh pit example actually relates to something that actually happens in real life? Yeah. Yeah. It's just a really good analogy that, you know. It'd be great to like take my chemistry class on a field trip to a mosh pit. Because we're like, this is gas law.
I think you get fired.
I wouldn't want to go.
Yeah. What I'll probably have to do is just show YouTube videos of mosh pits. Maybe when I do gas laws, I'll post a YouTube video of mosh pit, and you guys, and I'll be like, watch this and understand what's going on here, so that way we can talk about this in chemistry.
Yeah, you should make like a discussion about it. Like ask people what they think of what's going on in the video.
Yeah, that'd be good. Okay, example problems. Give it to me. I'll do one of them for you.
I need help on number 5.
Number 5. All right, read it to me.
Oh, it's just
It's a table?
yeah, it's a table.
All right, so you've got a table. And this is that table one. So once I give you one of them, you'll probably be able to get all of them. Let's do it.
Here,
You can just read it to me. All right, so number 5. All right, so what is it? It's
the
I'll tell you, I know which equation you can use. You can use Pervnert. PV equals nRT. Now this is a scenario. Oh shoot, that's too high. PV equals nRT. This is a scenario where you're not going to be doing something where you're not going to use PV over NT equals PV over NT. You're going to use this equation right here. And then number 5, part C, is saying, okay, here's the pressure, here's the volume, here's the N. What's the T? Oh, okay. So I gave you pressure, check. I gave you volume, check. I gave you N, check. Do we know R?
Yes.
Check. Do we know T? No. So I put a little question mark above it, maybe. Got it? And then solve for T. N and R I want to get rid of. Solve for T. I can't see what Madison wrote. I think she wrote PV over NT, or PV over NR equals T. Perfect. Now, in the problem, I gave you 4.47 atmospheres and 25 liters and 2.01 moles, and R is 0.08206. So you plug that into your calculator. Take 4.47 multiplied by 25, divide by 2.01, and times 0.08206. You want to tell me what the answer is?
405.
What is it?
405.
Oh, 405? 405 Celsius. Everyone cool?
That makes sense.
No, I'm not cool. 405 Celsius sounds unreasonably high.
You have to subtract 200.
This is 405
Oh,
Kelvin.
Yeah.
Did you?
Because remember,
But you
whenever
asked
we're talking
for-
about the temperature,
You
we're
asked
using
for
a
it
Kelvin.
in Celsius.
Oh, I asked for it in Celsius? Okay, so the answer. Wait.
So it is 405. You asked
Oh,
for it
okay,
in
okay,
Celsius.
wait. So the answer was like the when you plug this into your calculator, you end up getting like 678 or something like that. Kelvin.
Yeah, and then you subtract.
So you get 678 Kelvin. That sounds pretty high. But hey, it's high. And then I asked for it in Celsius, so you need to subtract 273.15 from this, and you end up getting 405. We cool with that? Why is that temperature so darn high? Okay, I'll tell you why. It's because I'm trying to look at this, and I'm like, man, 405 degrees Celsius, that's 4 times the boiling point of water. That's a pretty high temperature. But I'm thinking of this. if you were to solve what is the volume of a gas of 1 mole of gas at regular pressure, then it would take up 22 liters, 22.2 liters of stuff. Okay, I probably should give that to you as a problem, extra problem to do. But if you were to solve what is the volume of gas if I gave it to you at 1 atmosphere and actually, yeah, then and regular temperature, then it would be about 22.2 liters, right? Does that make sense to you? I mean, you just think about plugging in different numbers into this equation. And then I'm looking at this and I'm like, so I have a container that can fit 1 mole of gas normally. But how many moles of gas am I putting in there? I'm putting in 2 moles of gas, 2.01 to be exact. And am I putting this at regular pressure? No. Regular pressure is 1 atmosphere. This is almost 5 atmospheres. So think about this. If you have a mosh pit and you put twice as many people and they're running around, and the pressure is 4 times the amount, what do you think is going to happen to the temperature?
It's gonna get really hot.
It's going to spike up, which is probably why it's 400 degrees Celsius. So this is where it becomes like, wow, 400 degrees Celsius, that sounds hot. But then again, yeah, that's pretty good. I mean, that makes sense to me. By looking at the numbers. All right. Can I erase? Yes, no? Yes, okay, cool. All right. Let's switch hats. And I should wear a hat because my hair's crazy. Let's switch hats and we will move on to precipitation reactions because I heard that that's one that you guys really hate as well. Cool? Any other questions on gas laws? And remember, gas laws was my gift to you guys because because stoichiometry was getting too crazy for you. So you guys are like, I hate stoichiometry. I hate this. I can't do this precipitation reaction. I can't do this acid-base reaction, oxidation reduction reactions, and all of these different reactions. And so I said, well, hey, you know what? Calm down. Let's move on to gas laws. So if you guys are having a lot of trouble with it, I think you guys are just making it too hard. Now, I'll take responsibility for Tuesday because I put this thing out and I put the assignment out and I put in all of the right answers. Well, some of them. I think there was one that I messed up. But I put in the right answers. But what I did was I put too much of a constraint on it. I didn't give you guys enough margin of error. And technically, what I put down was correct because if you take into account significant figures, then you should have it as accurate as how I put it. But I decided to give you guys a little bit of leeway because to me, as long as I teach you about significant figures, you know what I mean? I think that's important, but I'm not going to burn you because it's just going to be unreasonably frustrating to do your homework. So I opened up the significant figures and I allowed you to put in like numbers that were a little bit further off from the actual answer. So that way it gives you a little bit of margin to play with. Cool? And I apologize for not doing that in the beginning. I will try to make sure to do that from now on. And yeah. And actually, by the end of today, my goal is to actually have the rest of the homework posted for all the way to the end of December, to the end of our class. All right, precipitation reaction. Any questions about it? Comments, concerns, vomits, etc.? I don't know how to do this. I'd like for you to do an example problem for me. This thing is so frustrating. What?
I don't know how to do it.
You don't know how to do any of it? Okay. Now, I've done problem number 1 to death. Can we work on a different problem? Okay. You ready? shake the mouse because you're probably gonna have to do that. All right. So precipitation reaction. Let me give you, like the gas laws. Let me give you guys the 10-minute spiel to show you what we're doing, and then after that, let me do a problem for you to show you the application of it. Are we cool? Now I have a question real quick. For those of you online, since you guys are so non-talkative, is this being helpful to you? Is this tutoring session? Okay, all right. Make sure you talk to me. I feel so alone. Even though there's like people surrounding me and I'm in a glass cage and I can't move. Yes, I still feel alone. Well, just because, I mean, I like talking to you. Because you guys are fun people. All right, you ready? Stoichiometry. This is the dreaded chapter 4, and you guys are all freaking out about it because it is hard. And I think I was talking about it with an actual chemist yesterday, and I think stoichiometry is easy. She thinks stoichiometry is easy. But I do remember a time, and remember I did chemistry 10, 15 years ago. I do remember a time when I really sucked at it, stoichiometry. And it really frustrated me. And I think that's where you guys are at. And then once I figured out, hey, that's what we're doing, oh man, this is not bad at all. Then it makes a lot more sense. And then it became easy for me. This is why your teacher and probably all of the people who are trying to teach you stoichiometry who actually get it, but forgot going through that painful process, does it. I think that once, and it's almost not a silver bullet that I can just give you. And so I can shoot you with a silver bullet and you'll understand it. You know what I mean? It's not a magic pill that I can give you. I can try to explain it to you as best as I can, but I think that maybe the best thing for me to tell you is that this, believe it or not, this chapter 4 is actually pretty straightforward. But the only way to really understand how it's straightforward is just to go through the painful process of figuring it out for yourself. And I will do everything in my power. I'm not holding some secret, I promise you. I will do everything in my power to give you it, but the only way to get it is just to frustratingly sit down and gruelingly do it. That's it. But let me do my best at showing you the overview, okay? For stoichiometry, we're going to need a balanced equation. And I covered balancing equations. And also, here's the thing. In the future, I think that what I'm going to do is I'm going to use a different textbook. Because I feel like this textbook, it assumed that you knew a lot of chemistry while I was trying to teach you chemistry. And I think that I would rather have it spend a whole chapter on balancing equations. And it didn't even have balancing equations anywhere in the textbook, so I gave you a worksheet to supplement that. And that, I don't know if that worked really well. But first, we need a balanced equation. And balanced equation is pretty simple. Like, for example, H2O2. H2 plus O2 gives you H2O. Well, here's the problem. Oh, shoot, you can't even see that. That's problem number 1. I'm going to combine H2 gas plus O2 gas to get H2O. Got it? There's too many O's on this side over here. So I need to put a 2O over here. Does that make sense? There's too many O's on this side. Because there's 2 O's over here, there's 1 O over there. So now if I put a 2 out there, there's now 2 O's on this side and 2 O's on this side. We cool with that?
Yeah.
The problem now is there's too many H's on the right side. So I'm going to need 2 over here. And that will kind of balance out my things. We cool? Do you understand how this is a balanced equation? All right. Now, we use this balanced equation. Here's what this game has all been about. In fact, I almost feel like I've been teaching you guys chemistry, and everything we've covered is all these conversion factors. I take a number and then I convert it, playing this game where I take the units and put, I make sure I know what's in the denominator, and then that goes and all of that kind of stuff. Are we cool with that? You guys remember this? This is like chapter 1 conversions, and then basically everything we've done in chemistry has all been with these big parentheses. This right here tells you very important information. These numbers in front, they're called coefficients. They tell you very important information. They tell you how to convert from pure hydrogen gas into oxygen, or pure hydrogen gas into water, or something like that. We can convert from the left side of this equation to the right side of this equation. When doing this conversion, you have to deal with moles. This is saying 2 moles of hydrogen gas plus 1 mole of oxygen gives me 2 moles of water. That's what this is saying, this balanced equation. You understand that? And you have to deal in moles. This isn't saying 2 kilograms of hydrogen gas plus 1 kilogram of oxygen gives me 2 kilograms of water. That doesn't work. You have to. This is specifically talking about moles. 2 moles of this, 1 mole of this, 2 moles of this. Now you can ask me, say, well, why doesn't it work? Why doesn't 2 kilograms of hydrogen and plus, if I take 2 kilograms of hydrogen plus 1 kilogram of oxygen, can I get 2 kilograms of water? Why doesn't that work? And my answer to that is, well, because the densities of hydrogen and oxygen will mess with you then. You know what I mean? Or the molar mass. If you have 2 kilograms of water, that doesn't, or of hydrogen gas, that doesn't necessarily mean you have, 2 moles of whatever. Or 2,000 moles or whatever. You know what I mean? So when dealing with a balance equation, you have to deal with moles. And then, so if I had my units over here as moles of H2, and I wanted to convert that into how many moles of H2O that would produce, I would simply look at these numbers right here. I would say, okay, moles of H2, moles of H2O, and then the number here is 2, and the number here is 2. So that would be my conversion factor. Or if I said something like, if I had moles of H2 and I wanted to figure out how many moles of O2 is required, O2, then I would write 2 down here and a 1 over here. Where am I getting these numbers, this 2 and the 1? Straight up from the coefficients up here. All right. Is that hard? No. That's easy. Everyone agree? You want to know a secret? That's stoichiometry. That's all we're doing. That's the big, hard, crazy thing that everyone is freaking out about. Yup. Now, what did she say?
Yes, easy stuff.
Okay, all right, easy stuff. Well, that's stoichiometry. Now, stoichiometry is not hard. That's it. I'm seriously, that's it. The hard part that you guys are having trouble with is, in order to get here, moles of H2, I don't ever give you the answer in moles of H2. I'll give it to you in grams.
So we have to convert it to moles.
So then you have to use the molar mass to convert to moles, so that way you can use this thing. Because you can't play this game that we're playing with stoichiometry, the easy game, if you're dealing in grams. You have to deal in moles. So you use the molar mass to convert from grams to moles, and then you can play this easy game. Another hard trick that I do, just to mess with you, because I'm a punk, that's why, is I'll give it to you in liters, and I won't give it to you in moles. You're moving that.
Oh, sorry.
Right. Well, then you'll have to use molarity to get it here. Molarity is a measurement of moles per liter. So you can use that to convert your liters to moles or moles to liter, vice versa. Does that make sense? Molar mass is a measurement of grams per grams per mole. So you can use that to convert grams to moles and moles to grams and vice versa. All right, here's another punk thing that I'll do. I'll ask you the answer. How many liters is it in the end, right? So after you do this process, you end up with moles as your units. And you're like, darn, I got to convert it now. Well, because he asked for the answer in liters from me. Okay, well, use molarity. If you have moles and you want to get to liters, use your molarity. Or here's another punk thing that I'll do. I'll ask for the answer in grams.
It's molar mass.
Well, then use molar mass to get from moles to grams. You went from grams to moles using the molar mass. You can go backwards. In this case, this is a matter of dividing, and in this case, it's a matter of multiplying by molar mass, but it's not really that hard. So this is what, a chapter 2 skill, and this is a chapter 4 skill. This right here is a chapter 4 skill, but that's easy, we've established. All right, and here's the last really punk move that I can do. I won't give you the balance equation. Well, then you'll have to go through and balance the equation on your own. So it's almost like stoichiometry in itself is actually really easy. It's getting all of the pieces of the puzzle together before you play the game that's hard. And it's not even that hard. It's just there's a lot of this is an easy step. This is an easy step. This is an intermediate step. This is an easy step, the stoichiometry game. This is an easy step and that's an easy step. So it's just a lot of stuff. And I think that maybe what I did when I taught you stoichiometry is I didn't show you this. I didn't show you, hey, this is essentially what we're doing. Right? So you guys are looking at this and you're like, well, when I solve the problem for you, I would go, well, I'm going to start here and I'm going to go through here and then using this, come back here and then doing this over here. And then this is all of the problem that I did. This is how you do it. It's easy, isn't it? Right? And you guys are like, I don't understand why he did that and why he took that path and where the hell he got all of that stuff from. Right? Sorry, my bad. I probably should have shown you this. But to be honest with you, if I showed you this picture when you didn't know anything about stoichiometry, I think that would have freaked you out too. Really, there's no good way to teach this thing, I think. I maybe could have given you guys a lot more training wheels when it came to balancing equations. Maybe I could have done this better at teaching to you, but at least now you understand. Hopefully that makes up for it. Cool. I apologize for any hair that you pulled out, but I honestly say you guys pulling out hair probably is the best thing for you. What I mean by that is you guys working hard at problems is probably the best thing for you. All right. Let's do an example problem. I think that when you see this in action, you'll be like, oh my goodness, this is not so bad. All right, give me a problem. And yeah, you'll probably have to pass the computer up so I can read it because there's just so many parts to these problems. Go for it online. Why don't you choose one? Come on, you guys hang in there. Okay, fine. Andre, why don't you choose one? Justice, choose one.
Looking for one with balancing equations.
All right.
So if you work on that. This one. Yeah, number 3.
All right, here, pass it to me. That's it.
Here's Victor.
Can you give it to me, Emily? All right, number 3. Okay, the mass of solid. What mass of solid silver bromide is produced when mixed with? Okay, so what you want to mix is AgNO3, AgNO3, and you also want to mix sodium bromide, NaBr. Got it? All right. May I? What is it? Hey, I have to go now. Okay. All right. You guys can. I'm recording this. Don't worry about it. All right. I'm going to start the problem, and then I'm going to ask for more details because I can't see those numbers as well. You just have to turn the computer on. All right. There's a table that I sent you an email about, and it's actually in your book. It's table 4.1. I told you you guys might want to take it and put it on your phone because I thought it was really helpful. The table says that, see this? So the first step I'm going to do is get the balanced equation. I need that balanced equation to play the stoichiometry game. Let's get there, okay? And then I'm going to erase all the work I did for that and put that balanced equation at the top because that's really the only important thing here. But we know that we're not even going to start the stoichiometry game. What we're going to do is we're going to get the first building block or the first tool that we need. When you bake, you need to get all your ingredients together. This is a balanced equation is our main ingredient, is one of our main ingredients. So I need to figure that out first. Cool? When you put this inside of a solution, what happens is this thing breaks apart into its ions. The reason being is because, according to that table, rule number 1 says all nitrates just don't hold together. So Ag goes into its ions, and NO3 also goes into its ions. I kind of want to try a harder problem, if that's all right with you. Can I see your computer, your big old computer? I'm gonna try one that has a oh my goodness, this is heavy. All right, here we go. Question 7. That looks good. Okay. Question 7. I'm dealing with M2SO4, and I'm also dealing with calcium chloride, so CaCl. Okay. Here. Ooh. All right, you're gonna have to hold on to that because I don't necessarily know. All right, I'm sorry. M2SO4 and CaCl. Okay. Now I sent you guys some emails. I need you guys to look this up on the table because, to be honest with you, I hate to say it, I didn't really memorize all of it. It's been a while. According to the table 4.1, I believe that this thing dissolves. SO4. Can you look this up for me? Sulfate ion. Look up the word sulfate ion. What's the charge on that? I'm thinking it's -2. And then, wait, this is manganese, isn't it? M, or no, what is M? Here, shake that thing again.
Yeah, it's -2.
Oh, we don't know what M is. M is just some weird thing. Okay. Yeah, this is a good problem. The reason why I think it's -2 is because this thing's positive. Well, this thing's +1, and there's 2 M's that have to balance out with this SO4. Does that make sense to you? So if I can look this up and say SO4 has a -2 charge, I can look that up inside of one of those tables that I gave you. And then I said, well, if that's the case, then there must be one, or the M, since there's two of those, must have a charge of positive 1. Did I make any sense there? All right. Calcium chloride, well, chlorine has a charge of negative 1. Calcium has a charge of positive 1. So I've got this substance here, and I'm adding it to this substance here. And when I put this in water, this thing breaks down into its ions, and this thing breaks down into its ions. Are we cool with that? And I think that the rule for this one is rule number 2. Isn't calcium a part of the alkaline metals, alkaline earth, or something like that? If you look up in the rule book, it says, oh, according to rule number 2, sodium, calcium, and the other ones that go inside that one column all break up. Are we cool? All right. Now, what I'm doing is I'm taking a solution of this stuff and a solution of this stuff, and I'm adding them together. So when I add them together, I can create a new compound. I can create a new compound that has the positives and negatives that go together. Are we cool with that? Because technically I could add these positive and negatives back together, right? I could just make it come back together with positives and negatives. But that wouldn't really do anything in my reaction because they would just fall back apart, right? Because according to the rules, these things fell apart. We cool with that? All right. Are we learning? Wait. Are we just assuming?
What is positive and negative?
Oh, okay. No. If you look up inside of your periodic table, it looks kind of like this, right? Remember the periodic table? I think calcium is here, isn't it? Confirm that for me, Justin. Sorry. Oh, Justice, yeah.
Yeah.
It's like right over here, right? It's in the second one?
It's in the second one. No, wait. No, you're right. It's on the far right side, but like not
Where's
on
calcium? It's on the far left side?
Well, depends. It's over here.
No, that's chloride. Where's calcium? Ca.
Oh, it's small. C. Oh, Ca. Yeah, you're right.
It's like over here, right?
Yeah. Right.
Remember, this guy has one extra electron. So if it were to create an ion, it would want to. Maya, 1 second, Maya. A seventh grader came in, right?
Yeah.
Yeah, bring them to this table. Okay. If it were to create an ion, it would create something like a positive ion, because what it wants to do is it wants to desperately lose that electron that it has. That extra electron is like, damn, I wish I could get rid of this electron. So it gets rid of this extra electron that it has, and so it forms a positive one. Yeah, this is calcium is in the first column, right? Or is it the second one? Oh, oops. I'm sorry. You're right. Then it's a positive 2. Then there's probably a Cl2 on this thing. Calcium chloride. Okay. So it has 2 extra electrons and wants to get rid of them. So the charge is positive 2. That would have screwed me up. Thank you for checking that. Now chlorine, I know, is in the one right before, in the column right before the noble gases, right?
Yeah.
So since chlorine is in the column right before the noble gases, it has a -1 charge because it's got 1 too little electrons to be happy in its outer shell. Does that make sense? Okay, so it's got a -1 charge. And so, can you look up for me calcium chloride? Just type in the word calcium chloride. And I'm hoping that you'll see the formula CaCl2. I should know that off the top of my head. I'm sorry, I didn't review all of the parts of this problem. I just kind of chose a problem that looked hard.
CaCl2.
Is that what calcium chloride is? Yeah, see? And the reason why I knew that is because Ca is +2, but Cl is -1. And so therefore, I'll need 2 chlorines to balance out with that 1 positive. We cool with that? All right. So, now what I'm going to do is I'm going to assume that this +1 goes with this -1, and then this one goes with this one right here. So, what I have is MCl plus CaSO4. Can you press the shift button on his computer? Right. And what I'm really curious to know is, as calcium sulfate. Wait, the precipitation of all calcium is dissolved in water and treated as excess aqueous calcium chloride. The resulting precipitate is of all the sulfate ions as calcium sulfate. All right, so what I'm really curious to know is, does this thing survive and does this thing survive? And I'll tell you, I don't think this thing survives. I think this thing breaks back down into its ions. But I think this thing does survive. And do you understand why I have 1 M and 1 Cl? Because I have the charge on M is plus and the charge on Cl is minus. That's what. Does that make sense? All right. And then I have 1 Ca and 1 SO4 because the charge on this is +2 and the charge on this is -2, so they balance out. Cool? But I didn't balance my equation yet. So you're telling me that if I started off with M2SO4 plus CaCl2, that would yield MCl plus CaSO4. Right? Now just do a quick check. Do I have the same number of stuff on the left as I do on the right? I'm realizing that you guys are looking at everything backwards.
Yeah.
That must be freaky.
It's kind of hard.
Someone log online. I'm sorry, I told you not to log online. Someone log online. That way you guys can actually watch my computer screen. Because the computer screen has it going forward. I'm sorry. You guys are like, what the heck is he writing down?
Yeah, so I was asking him. I was like, is that a L?
All right. There's not the same amount of stuff on either side. One side has 2 M's, and the other side only has 1 M. So I'm going to have to put a coefficient of 2 out in front here. We cool with that? But that takes care of things because this side also had 2 chlorines, and this side only has 1 chlorine. So that 2 out in front saved my butt. We cool? And then the CaSO4, that balances out. So what is my balanced equation? It's this thing right here. There's a 1, a 1, a 2, and a 1. I think that makes sense. To me, at least. Does it make sense to you?
Yeah.
Okay. All right. So I'm going to write that at the top. That's ingredient number 1. One M2 SO4 plus 1 CaCl2
Thanks.
yields 2 MCLs plus 1 CaSO4. I just rewrote that. That's all I did. Okay? All right, let me see the problem again. Emily.
Why is there a line right here?
I don't know. I think that the computer got a little bit messed up. Is there? Do you guys see that line?
No.
No, it's fine.
What's wrong? Is it hard to see?
No, it's just my computer's about to die.
Oh. It's not one thing; it's the other, huh? All right. Can you press shift? I can't see it. All right. So here's the problem, though. I gave you guys 1.42 grams of M2SO4. And I also said the precipitate that was formed is 1.36 grams of MCl, because this is my precipitate, right? So here's the thing that I did to mess with you, is I said, well, I didn't give it to you in grams, I gave it to you in, or I didn't give it to you in moles, I gave it to you in grams. And here's the incredibly crazy part, I didn't even give you guys the molar mass of M. Man, this is a hard problem. What a jerk. So what you're going to have to do is, I guess maybe here's the thing. If I knew the molar mass, let's say, oh wait, it was 1.62 or 1.36? Okay. MCl. Okay. If I knew the molar mass of M2SO4, I don't know it, but let's say what happens if I knew it? So we'll call this molar mass 1, and if I knew the molar mass of MCl, so we'll call this molar mass 2. What I could do, I'm late. Okay, all right, you can go too. All right, what I could do is I could take this problem, 1.42 grams. I could convert that into moles by dividing it by the molar mass of 1, as measured in grams per mole. And then I can say, well, that's equal to, or then what I can do is I can play the stoichiometry game. And then I can say, well, I have moles of M2SO4, and I want to convert that to moles of MCl. So moles of M2SO4 converted to moles of MCl. Here's the hard part is I chose too hard of a problem, I think, to do as an example problem to show you, hey, this is so easy. Look, this is my stoichiometry step right here. It wasn't that bad. I just used one of these, yields 2 of those, right? Now I have moles of MCl, and I want to convert that back into grams of this thing. So I need to, let's see, if I have moles here, I want to multiply by M2. And then that's equal to 1.36. Well, that's going to be equal to 1.36 grams. Does that make sense? No, it doesn't make sense. Yes, it does make sense. No, you're totally lost. Okay, here, check this out. Remember that picture? Stoichiometry. You got to put in moles. It gives out moles. You remember that picture? And I told you, what if I give it to you in grams? You have to use the molar mass to get there. Yeah. And then what if I asked for the answer in grams? Well, you'd have to use the molar mass again to get grams out. So this is molar mass 1 and this is molar mass 2. That picture's not hard, right? That's what each step is. See, this is in grams. I use the molar mass to convert it to moles. That's what this step is. This step in the middle, that's the stoichiometry part. That's not hard. And then I use the molar mass to convert it out to grams.
Okay, that makes sense.
That's it. That's what this long, crazy looking math is. It's this picture. You understand what each piece is doing. We cool? Now, here's the hard part, is we don't know what molar mass 1 is, and we don't know what molar mass 2 is. Press the shift key again. Alright, so the hard part is, I know how to do this. What you would have to do is you have to say, well, what is S? What is the molar mass of S? Look up your periodic table. Oh, you don't have a periodic table? S is what, 14 or something? What is sulfur?
12 point. 12 or 12, 32.065.
It's 32 point what?
Yeah, 065.
32.065. And O is 16. And CL is what? 35, yeah?
Yeah.
It's 35,
35.453.
35.453. Okay. What I would do is I would figure out the molar mass of each of these things. But the problem is you don't know what, this is the molar mass of M2SO4. This is the molar mass of MCl. So you know what S is, you know what O4, you know what O is. You can multiply O by 4 to get that, but you don't know what M is. That's what we're actually trying to find. Got it? MCl, I know what Cl is. I don't know what M is. Here's the hard part. The hard part about this problem is I don't necessarily know what M is, so I have to solve for it. I have to figure that out. Now, if I did this algebraically, that would be tough. But apparently, this is an actual substance. This is a real substance, right? They just use a different letter to represent it. They could have put an X there, and it probably would have made a lot more sense if they just used a straight up X, because you're used to solving for X. That's all we're doing. So here's what I would do: is I know that M has a charge of +1. Does that make sense? So it's probably in the first column of your periodic table. What I would do is I would choose different M's or different atomic masses of the different pieces of the different elements in the periodic table, and put that in for my M over here, and see if this equation works. Because only one of them will have the correct amount of atomic mass. And when you do that, then you can find exactly which one it is. That's what I would do. And I don't have a calculator, I don't have a spreadsheet on me to be able to show you how to do that. So I chose a poor problem for an example. Actually, it wasn't a poor problem. It kind of still showed you the basic gist of it. It just added a whole bunch of other steps that it's like, wow, that's not fun. So we cool with that? All right. I hate to say it, but I gotta work on I gotta work with my 7th graders now. So I don't mean to be discouraging, but that's basically the gist of things. All right, cool. I will try to post this to YouTube. Hopefully, this thing doesn't screw up in saving the file. Save it.